Hello everyone. Today we're going to be talking about the Polkadot ecosystem. There are going to be two videos on the ecosystem. Today we're going to be talking about Substrate, which is a framework in Rust to develop your own blockchain or a parent chain to Polkadot or Kusama. And there's going to be another video on Ink specifically. Ink is a smart contract template language using Rust to develop smart contracts that are native to Substrate. Some Substrate chains also support EVM, as we'll talk about, but Ink is the preferred language when we're developing exclusively for the Polkadot ecosystem. So about Substrate. Substrate is very complicated, even for Web3 developers. Why is that? Because most developers are used only to programming smart contracts into Ethereum or other chains. And smart contracts have a lot of safety features. For instance, you can always roll back the state. They are always guaranteed to work with the security of the blockchain. And those things are not given here in Substrate. Substrate is one level of abstraction below smart contracts. So you have to worry about things like consensus, crypto economics, and other ways of keeping your network working, even in the face of adversaries and hackers. So we have to think about this when thinking about Substrate security as well. So keep in mind that this is indeed more complicated than a simple smart contract, and it requires a more sophisticated team and better engineering to pull a full Substrate chain into production. Thinking about the main problems that we see into Substrate, I divide them into 7 categories. And it's essentially, most of them regard either crypto economics, or in other words, how you protect your network from attacks by creating incentives, and logical flaws. Logical flaws are flaws in the logic of our application that cause it to have bugs. And we're going to go through each one of those. Essentially, they're going to be third-party pallets, the parents of weight, storage, and fees that are very crypto economic wise. You have panics and input validation, which are more programming problems. And finally, logical bugs, which are bugs in the way the application is designed. So let's get to it. So first, talking about third-party pallets. In Substrate, you're able to use the frame to use a lot of ready-made pallets into your Substrate chain. And when you pull those pallets, they can be made by third parties. Whenever you integrate a pallet into your chain, you have to keep in mind that the integration of a new pallet is able to hijack your entire application. So if there's a flaw into the pallet, this flaw may cause the entire chain to crash, to suffer denial of service attacks, or even to cause state transitions and essentially all transactions to have wrong results. So to cause wrong state modifications. So whenever you use a third-party pallet, it's very important to first check if it has been audited and if it is from a reliable source. And second, check if there are either parachains or full Substrate chains that use those pallets and that are live for a long time, that have big investment funds behind them, and that have been exhaustively tested. Because if they don't have those features, it's very risky to use those pallets. This also applies for you when developing your own pallets. As we'll see here, you have to take care of a lot of things, because one single flawed pallet may influence how the entire application works and cause your blockchain to have security vulnerabilities. So keep in mind that other pallets have to be thoroughly audited and tested before you can use them with safety. So now let's talk about weight. Weight is a very important parameter into your blockchain because it is one way to measure physical resources. So when you're working with a blockchain in smart contracts or transactions, you're abstracting away. You're thinking about a chain that exists in a decentralized manner and that is independent from any machine. But when we're implementing the blockchain itself, we have to remember that each computer, each server has a limit in memory, in processing power, input-output throughput, and networking, and all other physical characteristics. So those have to be taken into account when developing your node. And essentially, weight is the way that the Substrate framework deals with both processing and input-output from file storage. So weight is a measure of how much compute time you need to perform certain activities, how much time you need to compute to perform a certain function call, to perform a certain operation into the blockchain. And each block that's going to be mined, validated actually, has a full block weight. So let's say that this block weight is, let's say 1,000, for instance. If block weight is 1,000, it means that the node can only fit 1,000 worth of weight inside a block. And a block takes an init value and a final value to start creating the block and finalize the block. Let's say that they are both 100. So that means that the block has only 800 wait available to process all extrinsic transactions. So this means that this is the time that the node has available to produce the block. And what's the problem here? So whenever you create a functional call inside of Pallet, inside your substrate node, you have to indicate how much weight that call is going to consume. And this is not so straightforward. If you just put like a random fixed amount of weight, you might be falling into a trap. So every time you input the weight that's going to be required for each transaction, this number is going to be taken into account by the node, and it's going to calculate this time based on the input that you said. So if you said that transaction A costs 100 weight, the node is going to try to include it in here, costing 100 weight, and so forth. The problem arises when you put the wrong number in there. So let's say you put 500 weight for a transaction, but in reality, that transaction is doing a loop over an unknown amount of elements. Let's say every time someone does a transaction, they add another element to the chain, and when you have more than 50 elements, the loop gets so large that it consumes more weight than you have previously indicated. What this means is that the node is going to try to include a transaction with a weight of 500 here, but it's actually going to have a larger weight, let's say 800, so it's going to fill the entire block. And when this kind of thing happens, what happens in the end is that the node is not able to finalize the block in time because it has more transactions to process than the block time. And it eventually makes the node DOS because it might get slashed. Once it does not produce the blocks in the regular time, it's going to be not following the protocol. And because of that, they can have their stake slashed into the proof of staking system. And that might lead the nodes to stop working. So this is a vector for denial of service attacks. If a hacker discovers that one of your functions consumes more weight than you have indicated into the programming of the substrate node, they are able to repeatedly keep calling this function until your nodes crash. And this is a very serious vector attack. It's sometimes hard to discover because sometimes you do calculate your weight using formulas and using benchmarks, but your calculation is wrong somehow, and this leads to this fault loss. So weight is very important. You have to be very careful. Always benchmark your weight and always consider the worst case scenario. So let's say if you're looping over an unknown amount of items, you have to consider a very large amount of items. You have to cap that amount at a certain value to make sure that this is never going to happen, because this might break your blockchain. So still talking about how the node is a machine that has resources that are limited, and you have to think about this when developing your parachain or your standalone blockchain. Let's talk about storage. So in the same way to have processing and I/O as limits in the node performance, you also have storage. The node cannot store in its memory an arbitrarily large amount of data. It has a limit. After that limit is reached, the node is not going to be able to operate anymore with simple machines. It's going to get more and more expensive until it gets impossible to store the data, and the blockchain cannot run anymore. So you cannot let the state of your blockchain get too large, otherwise it's going to be impossible to run the nodes, and your network is going to get a denial of service. People are going to start running the nodes, and the blockchain is going to stop working. So how do you prevent that? So let's say you have a theoretical limit on the max state size. You can actually estimate this and benchmark this by using a model machine. So let's say your model machine is a server of specs ABC. You can test it out and see how large the state can get before that machine starts to crash. But the idea is essentially that a malicious attacker is able to call a lot of different extrinsic functions into the blockchain that add more data to the state. And if they want to make your chain stop working, to do a denial of service, they can simply submit a whole lot of transactions until it fills out all the available space, and the node stops working. So they can just do a DOS. It's kind of similar to how a web DOS happens when there's a lot of traffic and your server gets down. So it's kind of similar. And how do you prevent this? So the way to prevent this is to not allow people to bring more storage until everything gets filled up, but with economic incentives, not with restrictions, because you cannot restrict people from doing legitimate transactions in the blockchain, but you can restrict the cost that they have to do it. So let's say you're able to create a new account to the blockchain just by creating it with cost 0. If this is the case, you can just bloat the state and make it all be filled pretty quickly. But on the other hand, if I say that to create a new account, you actually need to deposit 100 tokens into it, then it's not free anymore. And if someone wants to DOS the blockchain, they're going to have to buy a whole lot of tokens, which is going to send their price skyrocketing, and it's not going to be economically feasible for them to do this attack. So the lesson here is you always have to charge money, like real money, like real resources or things that cost money, to allow people to insert new state into the blockchain. If you don't charge them in any kind of monetary way, then they are simply going to DOS your blockchain as soon as it's a good idea for them. And some of you might think that, okay, they're going to fill the state, the blockchain is going to stop work, but what do they get with it? And it might not be very logical, but you have to remember two things. First, there are a lot of hackers that only do those kinds of things to mess up with projects and to prove that they can. So yes, you can get hacked in this way, but also we're talking about financial markets. You're probably going to have some tokens in your blockchain. It is possible that this hacker shorts those tokens into an exchange or bets that their price is going to get lower and does the hack so that your network goes down and your token loses value and they make money from it. So it is possible to profit from this as well. So be very careful with this, and every time you insert new state into the blockchain, you have to charge something. It has to have some kind of economic cost, otherwise it's not going to be possible to stop those DOS attacks. Yeah, so one important question here. My partner just asked, so what if the transaction cost is very low? Let's say it's 0.00001 cent. Does that still hinder the attack? And the answer is, it depends. It's always possible to pay the cost to do this. So you have to evaluate what the reward is for the hacker. So they have a reward and they have a cost. If reward minus cost greater than 0, you are subject to the attack. So let's say it is very cheap, so to bring down the whole network is going to cost me, I don't know, $2 million. And I can make a position into Binance with the token that I'm expected to make at least $10 million by shorting the token and bringing the network down. Then you're in risk of this happening and you have to increase the cost here, otherwise you're going to get hacked. But let's say that there's no way to profit from this, like the max thing you can do is make like a couple $100,000. Then you're safe because the hackers will be spending more money than they will be getting from the attack. So this is in the end an economic defense. It's like the Bitcoin defense. It's like Ethereum, any proof of stake system. You are only protected if the cost of corrupting the network is smaller than the gain you have from doing it. So it's possible for a super state, a big government, to just buy a lot of servers, get a hashing power greater than all Bitcoin miners, and kind of destroy the network. It's possible, but it's very costly and it's not worth it, and that's why it's protected. So this is what you have to keep in mind. This is not an absolute defense, it's an economic defense. And this is the principle behind blockchain. It's not only the computer science, but also these economic incentives that align to make the network secure. So still talking about crypto economics, we have fees as another mechanism of defense. So the fee you pay for a transaction is essentially a base fee plus the cost of the weight you're using in the transaction, plus the length of the input, plus the optional tip for you to have priority into the processing of a transaction. What this does is, this cost is also a protection. You have this cost to stop people from spamming the network with a lot of useless transactions. So let's say, for instance, that I enable smart contracts into my protocol, and someone just creates a smart contract that does a whole lot of loops with no purpose at all, a lot of hashing, just to consume processing power from your node. And they keep calling this function all the time until your node gets overwhelmed by information and no normal user can go there and submit a regular transaction. What happens in this case? You just got a denial of service. Your blockchain is not working, and this happens a lot, especially the blockchains that have a small cost per transaction. So that's why it's important to have a cost that is significant so that people won't spend the network, but at the same time it's not high enough to stop people from using it because it's too expensive. So you need to strike the balance. And one of the keys to strike this balance is the fee multiplier update. So we can actually increase or decrease the cost of weight based on the demand of the network. So you can create a mechanism inside your substrate chain that alters the fees for the same transaction depending on if the network has been spammed or not. And this is very important because it helps you strike the balance. Because if hackers know that if you try to spam the network, the fee multiplier is going to kick in and it's going to charge a whole lot more, that's going to make it so expensive that it's prohibitive to do the attack, they're not even going to try to do the attack. So they're going to keep the traffic low. And then regular users that are not trying to spam the network are going to be able to enjoy cheaper prices. If you don't use this, you need to create a higher fee from the start to stop people from spamming the network. So this is a way for you to protect the network without having your users pay way too large fees without needing to. This is basically one of the most important things into blockchains, together with the storage and the weight issues, and they essentially mean how you protect your computing resources from hackers and malicious attackers by creating economic cost. So fees, weight, and storage are three things you have to think a lot about when building your parachain or your standalone substrate chain. Another common misconception that people have when they come from a smart contract developing background and start developing on Substrate is on panics. So a panic in Rust is an unrecoverable error that halts the execution of the program. Essentially, in a smart contract, when you have such kinds of irrecoverable errors, you create a revert. So the transaction is rejected, and all the state modifications that came from the transaction are rolled back. So essentially, smart contracts have no side effects on errors. If you have an error, it's simply going to be ignored by the blockchain state, and you can safely resume without thinking about it. On Substrate, it's a different history. Essentially, there are two things that can happen if you get a panic. The most common thing is a denial of service. So simply the node will stop running. It reached the panic, it's going to stop running, maybe it's going to reboot, and it's going to panic again, and keep offline, and the chain's not going to work, so you're going to get denial of service. And in some cases, it's also possible to get invalid blocks. If this panic happens inside some parts of the runtime, it might create invalid blocks. DOS is a problem, but this is a bigger problem, because this is going to cause your nodes to produce wrong blocks that are going to get propagated in the network, and this might get them slashed, or might get the network to form forks with different invalid blocks, and this might fuck up the entire blockchain. So it's very important to avoid panics. You cannot have any situation where you're going to have panics inside your Substrate code. So this is very important. It's not like a smart contract. You can just panic and have the errors, have the state resume to the last valid state. Here you have to take care so that everywhere in the code there's no possibility of causing a panic, because panics are going to make your node stop working. This one's a more classical computer science problem. It's input validation. Essentially, there are two things that can happen here. One's overflows or underflows, where you have a number that might get larger than the maximum number and cause it to either panic or to wrap around, which is going to cause undefined behavior, and also unexpected values. For instance, let's say you have a transfer function to transfer assets, and you're not expecting anyone to ever input 0 in there, but if you put 0 in there, it might cause some unexpected behavior as well. So these are situations where your input might have values that cause the program to behave in an unexpected way. And this, even though it can be hard to predict, it's actually very easy to test, because you can always use a fuzzer. So this is very standard for safe development, and it's a good practice to incorporate into your testing and into your code reviews. So use a fuzzer. You can use Cargo Fuzz or other Rust fuzzers to test out all the functionality into your protocol by inputting a lot of random values and checking if one of those random values is going to generate a different result than expected. If this happens, then you know you have an overflow problem or some validation problem, you have to fix it. So we run those in our audits as well, but it's something that you should run inside your development practice to keep your code more secure. And finally, after considering all different scenarios I just told you about, cryptoeconomics, computer science problems, and even third-party reliance problems, we have the logical bugs. And these are by far the most important, most common, and hardest to debug. When you have these problems, essentially your blockchain just works. It's not going to get a DOS. It is going to be sound in a crypto-economic way. But the problem is that what you're trying to do in practice, the application you're building doesn't really work well. And how can that happen? So some examples are, for instance, sensitive data. Let's say you have an application that's storing sensitive data on chain. That works well, it's going to perform its function, but anyone can go there and read the data and get access to it, because you designed your application in a way that doesn't work, because the blockchain is public. So this is a logical bug. The logic that you used for your application is wrong. Another example, race conditions. Let's say you post a riddle on the blockchain and someone has to submit their guesses on what's the correct answer. And the first to submit the guess wins. There's a race condition problem here, because if I submit a guess myself and it is correct, it is possible that someone checks my transaction before it gets accepted into a block, builds the exact same transaction, and manages to get that transaction into a block before I do, either by paying a higher tip, by running their own node, or by being closer to other nodes. So there are a lot of ways in which you can actually cheat the application. So this is also a bug because people can cheat the application because of the way it is designed. Another example, math problems. Let's say you implement a formula to calculate rewards in a staking program that allows some people to steal all the funds if they fulfill some kinds of weird criteria that you have not predicted. So there's might be an error in your formulas. It works well, it does what it's supposed to do, but what it's supposed to do is wrong. So you get errors from that. This is also very common with cryptography. Sometimes you use correct cryptography primitives, but the way you use them doesn't really work. It leads to flaws. And this is a very big problem, and this is not something you can just prevent. This is where most of the time of the author is spent, is in trying to imagine different ways in which your program can fail and it can be exploited and testing them out. The only way to really guarantee you don't have any logical bugs is by testing everything out and leaving your application in production for a long time. So authors are going to be going through those and trying to find as many as they can. And it's always possible that there's some very hidden thing here that doesn't really work. So the only way to be sure that there are no logical bugs is to have your application run for a long time without any exploit and have a lot of different audits in the middle of it. And something that might also help is formal verification, but that's a very different technique that is very expensive and not really easy to do on blockchains. So essentially, this is something you have to worry about. Test your applications out for as many scenarios as possible. Get as many audits as you can. But this is the most difficult thing about security, is guaranteeing that your logic is ultra sound and doesn't allow anyone to exploit your blockchain. Well, guys, so I hope you enjoyed the presentation today. We're going to have another one coming about ink. And please feel free to drop your message in the chat here, or talk to us if you have any questions, if you want to audit your code, or if you want to do some content, have a chat about technology, anything. We're here to talk, and thanks for your attention. Have a great time.